Hello, guys. Welcome to Ramta Solutions. Welcome to your grade 12 physical sciences exam prep on electrodynamics. In today's video, we are looking at a question paper by the Department of Basic Education. We're looking at their physical sciences paper 1 of November 2024. Okay. So this question is 13 marks in total. So we must take exactly 13 minutes or lower. Remember, but for the purpose of this video, we must finish at exactly 14 minutes or lower. So let's see now. Question 9. The graph below shows the induced current in a generator. Shows how the induced current in a generator varies with time. We can see that. We can see the maximum current. 9.1. Name the type of generator. Choose from AC, DC. As you can see here, it is not exhibiting a sine or cosine graph. So this will be a direct current. So it is DC. Okay. Proceeding. State the energy conversion that takes place in this generator while it is in motion. For a generator, it will convert. So generator converts mechanical energy to electrical energy. Okay, converts mechanical energy to electrical energy. Okay, to electrical energy. All right. Now let's see, state the energy conversion. So you don't have to say convert, you can simply say mechanical energy to electrical energy. That's okay. All right. Now, give a reason why this generator is not suitable for transmission of electricity over long distances. This is a DC. The reason why it cannot be suitable, it's because one is because it cannot be stepped up or stepped down. Okay? It cannot be stepped up, or it also cannot be stepped down, or cannot be stepped down. Maybe let me say cannot be stepped up or down. Okay, it cannot be stepped up or down. And another reason could be the energy losses with this kind of generator cannot be reduced. Okay, they cannot be reduced. All right, perfect. Now let's go to 9.4. Let's go to 9.4. Remember, for 9.3, before I proceed, there are many reasons. One of them is that it cannot be stepped up or stepped down, right? And the energy losses cannot be reduced. And generally, transformers do not use direct current. Okay, perfect. Now, calculate the frequency at which the coil rotates in the generator. In grade 10, when you spoke of frequency, you said it is the number of waves that are passing per second, or that are passing a point per second. All right, the number of waves or pulses that are passing a point per second. So when you look at this is not a complete wave, it's half a wave. As it gets here is a complete wave. Okay, so you do recall frequency equals 1 over period. So the period to complete one cycle is 0, 0,02. So what is 0,02 over 1 divided by 0,02 will be 50 hertz. All right, it'll be 50 hertz or 50 per second. But otherwise, because it's frequency, better to say 50 hertz. You can also say 2 over 0,04. It's the same thing. Okay. You can also say 2 over 0,04. It's the same thing. Okay. All right. Now let's go to number 5. This one I can see it looks like it was an easy question. I don't know why, but let's proceed. Define the term root mean square current. What is root mean square current? So root mean square current is the alternating current, right? Is the alternating current that dissipates the same amount that dissipates the same oh, that dissipates the same amount, right? That dissipates the same amount or the equivalent amount, right? Let's say that dissipates the same amount of energy as an equivalent direct current. Okay. Okay, that's an equivalent direct current. So we are on the 6th minute, approaching the 7th minute. We are on track. So this is root mean square current, alternating current that dissipates the same amount of energy as the equivalent direct current. 9.6, let's go to 9.6. Calculate the root mean square delivered by the generator. You can see here the maximum current is 1,2. So root mean square current is equal to maximum current over square root of 2. Root means maximum current is 1.2 amperes. Okay, so 1.2 amperes over 2. What is this? So 1,2 amperes over square root of 2 will give us 0.85 amperes. 0.85 amperes. Do you guys see that? This is 0.85 amperes. Right. Perfect. Now, 9.7. The graph below shows how the induced current varies with time after a change was made to the operation of the generator. Wow, fully describe the change that was made. So, what you are seeing here, one, you are seeing that, for example, frequency was halved. Do you see this? But should I say frequency or should I say period? Maybe let me say, as you can see, the period was 0.02, but now it's 0.04. So what do we say? Do we say the period was halved? No, the period was doubled. All right? So the period was doubled. What this means is that the frequency was halved. All right? This is to say the frequency was halved. Right? Frequency was halved. Right? Frequency was halved. All right. So, what are the things that can make this to really be? It could be number of coils being decreased, speed of rotation being decreased, and the strength of magnets being weakened as well. Right? Those are things that can affect this. So, what is happening here is that the frequency was doubled. The frequency was halved. That is to say, the period was doubled. Right. These are the changes that were made. Okay. All right. So, this is it, guys. This is how you answer this question. Okay. This is how you answer this question. Remember, I said what can make this to be could be reducing when the frequency is halved. What does it mean? It means it's a bit slower now. All right. Isn't it? It means it's a bit slower now. All right. So when that is done, that means you have changed your number of coils. You have decreased them. You have decreased the speed of rotation. You've also used a weaker magnet. All right. Or weaker magnets. Okay. So this is it. We're done. And see you next time. I believe we still have more exam questions that we're going to treat. So that is it, guys, and bye bye.